Good morning, everyone. Welcome back to lecture number 6, if my counting is accurate. Let me give you a brief reminder of what happened yesterday. We took advantage of all the CFT tools we have developed at the beginning to covariantly construct the spectra of open and closed bosonic strings in Minkowski background. And the reasoning was that everything we say about a physical state should be compatible with the diff-cross-Weil invariance. In fact, the diff-cross-Weil invariance of the Polyakov action is one of the most holiest features of the bosonic string, because among other things, this is the key to decouple negative norm states. I mean, this is the challenge which in a first step at a covariant canonical quantization doesn't come that easily. And with the CFT toolbox, this could be worked out without dealing with divergent sums. And the way the construction went in more detail was, for each physical state in the spectrum, we wanted to have a field equivalent. I mean, this is always working well in a conformal field theory. There's a state operator correspondence. For each state in the theory, there is a corresponding operator or a field whose asymptotic value at past infinity generates the state. So instead of giving you the physical states, I'm giving you the physical vertex operator, the field equivalent. And as I said, these vertex operators are required to give you a diff-cross-Weil invariant upon integrating. And in the closed string case, we clearly integrate over the entire world sheet. So this is giving you a d square z integral with 2 real dimensions. And in the open string case, the vertex operator is supposed to be inserted on the boundary of the world sheet. We talked a little bit about the boundary conformal field theory description of open strings and their world sheets. Yeah, so here it's enough to do this dz integral, 1 real dimension, a contour integral over the world sheet boundary, or we will refine that later today, that for a given dependence on the Chen pattern factors, you have a segment of the real line that you integrate over. Yeah, so integrating is a necessary condition to potentially get a diff-cross-Weil invariant. But you need to work a little bit harder. You need to ensure that the thing in the integrand transforms in the opposite way as the integration measure does. And that's tantamount to saying this vertex operator V should be a conformal primary. So in the closed string case, it's an old school conformal primary of weight h and h bar both equal to 1. And in the open string case, we have to pay a bit more attention what it means to be a conformal primary. So in the open string case, this is in the cosmos of boundary conformal field theory. So here we talk about those conformal transformations that preserve the boundary. In our favorite parametrization, the real line. So you have to construct an energy momentum tensor adapted to this situation. But okay, so for the computational practice, this is not playing that much of a role, as you will see later, but I wanted to make sure that you have all the foundations spelled out in a tidy manner. Yeah, so in the open string case, there is only one energy momentum tensor component to which we need to pay attention, and the vertex operators need to be, again, primary fields of weight 1 with respect to this T open. Yeah, fixing the conformal weight and keeping in mind that there should be a plane wave as part of the vertex operators, we can determine the mass spectra. I mean, each of the vertex operators were conformal weight times some decoration, where the decoration is only containing differentiated versions of the field X. So these decorations were the field equivalents of the alpha oscillators with subscripts -1, -2, and so on. So these oscillators clearly can only contribute integer units to the conformal weight. So this discreteness, this story with the integer units coming from the oscillators, this gives rise to discrete mass spectra. So in the open and closed string case, there is a different scaling by a factor of 4. This has to do with how you get from open string Green's functions to the closed string once and back. But setting these factors of 4 aside, the spectra are looking almost identical. You have a single state with a negative m square. This is when the vertex operator is only the plane wave and nothing else. And then there is a collection of massless states. This is where we find gravitons in the closed string case and gauge bosons in the open string case. And then there are infinite towers of positive m square states. And the explicit form is getting combinatorially more and more involved. You have a lot of options to put different derivatives of the free boson X into the vertex operator. But I guess the physically most interesting question is how the massless states interact and how string theory introduces corrections to the gravitational interactions here and non-abelian gauge interactions there. Yeah, when looking at the complete set of massless states, we also found a so-called B field and a dilaton in different Lorentz irreps as compared to the graviton. Even if you haven't heard of them yet, I can assure you that you can still recover good old Einstein gravity at tree level, because the extra states, the B field and the dilaton, they only couple in pairs to the graviton. At loop level, there is a bit of work needed to decouple those, and that's actually quite a vibrant discussion topic in various communities. But I think there's an increasing amount of progress to decouple dilatons and get back to Einstein gravity, say when it comes to computing loop corrections to gravitational interactions from string theory methods. And over here, well, the massless states contain the gauge bosons and also some scalars. So there the counting depends a bit on what kind of DP brane you investigate those. We discussed the possible boundary conditions on the endpoints of open strings. There were the two options of Dirichlet and Neumann boundary conditions, separately in each space-time direction. So you solve all the consistency conditions for various choices of how many Dirichlet conditions you want to have. So this confines the open string endpoints on a hypersurface in space-time, so-called DP branes. So P is the tunable number of spatial directions covered by the DP brane. So if you take a space-time filling D-brane, well, I didn't discuss it, but that's satisfying the consistency conditions we discussed, then you really have a gauge boson in D space-time dimensions with D minus 2 polarization degrees of freedom. And then if you choose DP branes of increasing codimensions, then there will be more and more scalars associated with the Dirichlet direction polarizations. And if you, for instance, pick D3 branes in the 10-dimensional superstring, you have a fine-tuned number of 6 such scalars, and these are exactly the ones in the n=4 super Young-Mills multiplet, which I guess you learned more about from Alberto this morning. Yeah, I hope this was covering most of the highlights of the previous lecture. Are there any further questions on this, or shall I go into the new material? Okay, then with one more sip of coffee, let's start the discussion of scattering amplitudes. So the rough idea about scattering amplitudes in string theory is sounding similar to quantum field theory amplitudes. The big question is what's the probability for various scattering processes to happen, regardless on whether these are point particles or strings in the external states. You want to ask the question for various choices of particle species, for various choices of momenta and other quantum numbers like Champatton factors, you want to ask what's the probability for this process to happen. And these probabilities are almost computed by scattering amplitudes. Well, they are just an absolute value square away. So you typically have to take absolute value square of a scattering amplitude. I mean, by itself, an amplitude is usually complex, so it can never ever cover a probability, but it's the absolute value square which informs probabilities. And I guess depending on your setting, say what you measure in a collider, for instance, you may or may not have to sum or average over various quantum numbers, depending on what you can measure and observe. So this is the rough intuition behind any kind of scattering amplitude. And a similarity between strings and QFT is the zeroth order idea how to compute them is to path integrate over all possible histories. And these possible histories come with different guises. There is, in the quantum field theory case, bookkeeping based on Feynman diagrams. I mean, summing over all admissible Feynman diagrams is a concrete realization of path integrating over all possible histories. And these Feynman diagrams are replaced in the string theory case by different string worldsheets. And most of the work is to make this more precise, what we mean by all possible different string worldsheets. So this will lead us to the so-called topological expansion of string scattering amplitudes. And let me draw a couple of figures to illustrate how different topologies can bring different contributions to string theory amplitudes, and where we can see certain analogies to quantum field theory. So we do a perturbative expansion of string scattering amplitudes, which is quite similar to the loop expansion in quantum field theory. And order by order, in some string coupling that I will explain shortly, order by order, we once more insist on diff cross Weil invariance of every ingredient. And furthermore, the sum over all histories should only go over diff cross Weil inequivalent configurations. I mean, if two histories or two worldsheets are related by a diff cross Weil transformation, then it would be a waste if we were to count both of them. And sometimes it would even be an infinite overcount. So that's a key guiding principle. Only diff cross Weil inequivalent configurations, please. Okay, and what are then possible topologies that could contribute? So here, let's assume for the moment that we are scattering closed string states, where all the external legs can be represented by infinitely long tubes. I mean, a spoiler at this place, in order to do computations, it's of course advantageous to map them to punctures to point-like defects, which I will also do in a couple of minutes. But just for a first look, it probably doesn't hurt to draw the worldsheets in the appearance with infinitely long tubes for the asymptotic states. And yeah, here are the possible topologies. I mean, this process of closed strings joining and splitting, this may appear on worldsheets with an arbitrary number of holes. So this is a concrete incarnation of summing over different histories. And as I keep on saying, there's an analogy to Feynman diagrams in quantum field theory. So let me also sketch those. This counting of different numbers of holes in a string worldsheet is analogous to staring at Feynman diagrams with different numbers of loops. So at tree level, for instance, without any loops, a 4-point QFT amplitude may involve Feynman diagrams like those. And then similarly, at one loop level, there can be here this box graph and other Feynman diagrams, say with a triangle or bubble. And a very neat connection between string theory and field theory at that stage is the following. So in particular, if you have massless states on the external legs, there is a neat and explicit way to go from here to there, starting from the mathematical expression for these worldsheet contributions. These are going to be functions of alpha prime, or dimensionless combinations of alpha prime and momenta squared. And if you then study the formal alpha prime to zero limit, kind of a Taylor expansion in alpha prime, then you recover QFT building blocks, including all the propagators of these tree-level diagrams. So here, I mean, only look at the genus zero worldsheet with topology of a sphere, and this is going to give you all tree-level Feynman diagrams. And then this can be done separately, loop order by loop order. So the alpha prime to zero limit doesn't mix between loop orders in string perturbation theory and loop orders in QFT. And let's say the actual appeal of that is, well, not only that you get the propagators of the Feynman diagram, I mean, everybody can write that down on the spot what the propagator structure is, but the real deal is to also get the polarization dependence coming along with that. I mean, suppose you are in Young-Mills gauge theory, where each vertex has several terms and several Lorentz index contractions, then it can be a lot of work to assemble all the kinematic factors. And string theory does that for you, and really throws out all Feynman diagrams at once with the corresponding polarization dependence. So there's really a lot of packaging work that the string worldsheet does for you. And this is getting particularly pressing at loops. If you have a supersymmetric theory, then there are a lot of cancellations between bosons and fermions in these loops. And all of these cancellations can be quite conveniently tracked at the string theory level, even before touching alpha prime. So string theory is really a fantastic way to give streamlined derivations of supersymmetric loop amplitudes in super Young-Mills theory and in supergravity. Say in the one loop level in n equal 4 super Young-Mills and n equal 8 supergravity, string theorists were the first to evaluate the one loop amplitudes, and it was quite a surprise back then in the 80s that the only graph surviving in the 4-point loop amplitude is the box graph. I mean, naively, you would draw all the triangle bubble diagrams and whatnot, and all of them could come with very different looking kinematic factors, but doing this through the string worldsheet gives you an extremely simple answer. It's the box graph and nothing else, and also its kinematic factor is fairly simple. Okay, so this is a connection between field theory and string theory, so far represented in the closed string picture. But okay, since I already mentioned that this works for n equal 4 super Young-Mills, you can probably anticipate that I was thinking about the analogous open string worldsheets. So in order to study gauge interactions in super Young-Mills from a string theory perspective, you do this move. And yeah, that's actually quite amusing that the same Feynman diagrams are reached from both open and closed string worldsheets. I mean, this one has no boundary. This one has a boundary, topology of a disk, and this has no boundary, the topology of the sphere. And this property, boundary or not, is getting washed out in the alpha prime to 0 limit. And as a particularly nice corollary of that, well, since you get the same Feynman graphs in gauge theory and gravity, there will be a relation between the respective numerators, the respective polarization dependencies. That roughly speaking, in gravity, the numerator of such a diagram is the square of the analogous numerator in Yang-Mills. I mean, just do the respective open and closed string calculations in parallel, and then these kind of squaring relations become apparent. So this is very well understood at tree level, fairly well understood at the one loop level, and there is an increasing number of examples at 2 loops and higher, and many people are working hard to find a all-encompassing formulation regardless of the loop order. Okay, so for instance, what I said before, only the box graph in one loop 4-point amplitudes. This you find also in n equal 4 super Yang-Mills coming from this open string worldsheet. And okay, to be fair, the open string has one extra diagram here, Möbius strip. Given that open string worldsheets have boundaries, there are in general more possibilities at a given genus for a given number of holes. And similarly, at the 2 loop level, there are even more possibilities. One of them being this diagram here. And then maybe another 4, 5, 6 diagrams which are related to this in the same way as the Möbius strip is related to that. But even with these few more, as I'm respectlessly writing here, the counting of these open string diagrams is extremely moderate in comparison to the cornucopia of Feynman diagrams which arise in the field theory limit. And yeah, in a pure closed string theory, there is literally a single diagram per loop order, namely the respective compact Riemann surface at genus G, with no boundary. Okay, yeah, as I was already saying, this is an efficient way to do Feynman diagram computations, and in particular, a single worldsheet at a given genus will spit out upon alpha prime to 0 all Feynman diagrams at that genus. So for the closed string case, that doesn't require more explanations. And in the open string case, yeah, both of cylinder and Möbius strip contribute to all relevant one-loop graphs. So this can be particularly valuable when the number of external legs grows. For instance, let's take as an example phi cube theory, or count the number of tree-level diagrams of a phi cube theory. The number of tree-level diagrams with only cubic vertices goes like a double factorial, where n is the number of external legs. Yeah, all of them come from a single genus 0 worldsheet, either the disk or the sphere. More precisely, the different Feynman diagrams, I mean the different channels, will be sitting in different corners of the moduli space of these string worldsheets. That is something I will try to describe in more detail later on. Okay, I keep on oscillating between similarities to QFT and differences to QFT. Let me be very clear about a fundamental difference to QFT. Fundamental difference between point-particle interactions and string amplitudes coming through this worldsheet method. So a little piece of Feynman diagram typically looks like that, where world lines split and join, and the analogous piece of string worldsheet would look like that. Okay, here this is the closed string example. And the interaction can be attributed to an isolated point in space-time here, with zero extent in whatsoever direction. So this is in the extreme short distance regime. And whenever there is a UV divergence in carrying out Feynman integrals, then you can blame this short distance regime, or you can blame the point-like nature of this interaction zone for it. And this is particularly bad in perturbative gravity if you derive Feynman rules from suitable expansions of the Einstein-Hilbert Lagrangian. And here in the string theory case, it's impossible to identify a single point in space-time of where the interaction happens. So you would look somewhere in this region, but it's actually not a diff cross Weil invariant notion where exactly an interaction may take place. So there is automatically a smearing out. And accordingly, the ultraviolet regime of string amplitudes is extremely nice, given that these short distance effects are no longer there or no longer invariantly describable. The ultraviolet regime of string amplitudes improves a lot. So they are, in fact, exponentially soft in the ultraviolet. So concretely, for closed string amplitudes, there are relatively simple arguments why you don't encounter any UV divergences in closed string amplitudes. At the mathematical level, it has to do with the so-called modular invariance of these Riemann surfaces at genus 1 and higher. And yeah, I think the intuitive picture is in all cases this one. And in open string cases, to get nice ultraviolet properties, you have to sometimes combine the different surfaces at a given genus. So here in the genus 1 case, for instance, it's the interplay of cylinder and Möbius strip, which tames the ultraviolet behavior of 4 gluon scattering at one loop. And this mechanism will also determine the gauge group for you, forcing you into an SO32 in case of the type 1 superstring.
Sorry, I have a question. We always said the non-string amplitude in the open string sector, only in the case of unoriented strings.
Okay, let me see. Yeah, how does it come about? Yeah, I think it's the orientifold projection that defines the type 1 superstring theory that introduces the Möbius strip. That's correct. Yeah.
So we have the Möbius strip only when we have an orientifold plane in our fixed side. We do this orientifold projection, not always.
Okay, that's right. That's right. Yes. So, right. If you really want to, you can do without, but then nobody will help you in the UV. Yeah.
Okay. But without the method, I have to consider only the cylinder amplitude.
Sorry?
Without the orientifold projection, I have to consider only the cylinder amplitude.
I think that's true. Yes. Of course, you have to be careful to have all the planar and non-planar configurations with insertions on both boundaries. But yes. There was another question?
Is the fact that we are getting only vertices with 3 legs due to the fact that we can always perform, let's say, a pan decomposition of the Riemann surfaces? Or could we get different number of legs for our vertices in the interactions, in the Feynman diagram?
I don't think there is a completely invariant way of deciding whether something is cubic vertex or quartic vertex. I mean, you usually look out for kinematic poles, one divided by Mandelstam ST and U, to decide whether there is a cubic vertex or not. And of course, you can always take a term without poles and insert an S over S. And then say, aha, I have a 1 over S, and the numerator happens to depend on S. You can also hide that by eliminating S in favor of T and U. I think this is, in general, highly ambiguous. Of course, you can be creative to cook up rules, what you absorb into a cubic diagram and what you absorb into a quartic diagram. And maybe that Pan's decomposition helps you to cook up convincing rules. I don't know. Yes, please.
What happens when we have in the low energy anomalous theory? The string diagram will recover the anomalous diagram of the H theory, or?
Sorry, you mean what the respective low energy limit is?
Yes.
Yeah. I mean, they both reduce to the Feynman diagrams. I mean, once you take alpha prime to 0, the worldsheets become very skinny. So this skinny limit, it erases so much information. So as I stressed before, skinny limit is the same whether you start from closed string, I mean, torus topology, or open string cylinder topology, and also the Möbius strip topology will have the same skinny limit. There will be an amusing mixing of different color orderings. I didn't get there yet to talk about how you should take traces of the Chen pattern generators. But yeah, given that the Möbius strip only has a single boundary, the skinny limit has a amusing mix of different color orderings. So once you are careful to disentangle those, then yeah, the skinny limit gives the same field theory building blocks. Yeah, there is yet another remark I wanted to motivate from this cartoon here. I mean, here this worldsheet sketch is presented in the context of interactions. So I'm telling you that this comes from interacting strings. But suppose you just look at a little portion of that picture. Suppose you zoom onto a little piece of interacting worldsheet. Can you still see that this is an interacting worldsheet? Or would you see the same as if you zoomed onto the picture I drew along with the Polyakov action when describing the free string? So where I'm trying to get is that locally, there is no difference between the free string and the interacting string. And this is very different to QFT. So the worldsheets of interacting string, it looks locally the same as the free theory. Oops. And more concretely, it means that the Polyakov action alone is enough to do all of these calculations for interacting strings. So the Polyakov action encodes the complete flurry of string interactions. You don't need to add any extra terms, as it is the case in quantum field theory. Say, for the Klein-Gordon scalar, you first write down a free theory, quadratic in the fields. Then you need to add a term to the Lagrangian that goes like lambda phi to the fourth, or whatever polynomial interaction you like. So in QFT, this is a by-hand process in most cases. Maybe the non-abelian gauge theory is a bit a borderline case where the symmetry is taking care of that, but nevertheless, there is an explicit cubic piece of Lagrangian and quartic piece of Lagrangian that inserts the gluon interactions, the cubic and the quartic ones. And none of that is needed for string theory. It's the Polyakov action, no need to have any nonlinear extension with respect to the free boson X. It's the free theory's worldsheet action that determines all string scattering amplitudes. Yeah. Good. You can could already hear that there is a strong field theory motivation to study string scattering amplitudes. But even if you are not interested in super Young-Mills, supergravity, and other alpha prime to zero effects, there are separate lines of motivations why you can learn a lot from string amplitudes. So a second line of motivation is of mathematical type, that there is a very fruitful interplay with number theory and algebraic geometry. These string worldsheets generate a lot of interesting numbers as you explore the alpha prime corrections beyond field theory. These are specifically the Riemann zeta function at genus 0 and a generalization thereof to so-called multiple zeta values. So this is a collection of numbers that play an important role in algebraic geometry. Like they are, in a certain sense, the most general integral you can get out of a genus 0 surface by integrating over its moduli space. And it has a lot of information on what algebraic geometers call a theory of motives, like a very abstract viewpoint on integrations with tremendous value for physics. And at loop level, these string amplitudes give a natural home to modular forms. These are functions of the complex structure modulus of a torus, and they are studied, for instance, in number theory. There are extremely cool properties associated to their Fourier expansion. Quite often, the Fourier coefficients count various physical quantities, like black hole microstates. And string loop amplitudes generate all kinds of modular forms. Some of them are having integer Fourier coefficients and participate in various counting games. But there are also other classes of modular forms which seem to go beyond the scope of that, which even have zeta functions or zeta values in their Fourier expansion. And to mathematicians, this was quite fascinating that such modular forms exist. And they are non-holomorphic, where so much less is known about classifications. So there were lines of research in mathematics inspired by what the low energy expansion of a closed string one loop amplitude has to say. So certain modular forms therein, called modular graph forms, inspired several papers that Francis Brown wrote in algebraic geometry. And it was extremely exciting to see how mathematicians give a completely different characterization of these function spaces of non-holomorphic modular forms. So some of the things that are obvious to string theorists are hard to digest in mathematics, but conversely, a couple of things were super obvious to Francis Brown in his math papers, and string theorists had a hard time digesting that. But it was so rewarding to listen carefully, and one can get so much predictive power by taking along the advice from mathematics. And I'm sure there will be many more such interactions for a higher genus where you get more general notions of modular forms, say vector-valued ones or modular tensors. This is mathematical line of motivation for string amplitudes. And then a third one, maybe a bit closer again to string theory, is related to string dualities. Okay, I haven't explained them in detail yet, but different superstring theories are related through a web of dualities. So, for instance, T-duality, when you compare different compactification geometries, and S-duality of the type 2B superstring, where you exchanged weak coupling with strong coupling. And all of these dualities work order by order in alpha prime. And computations of string amplitudes allow you to separate different orders in alpha prime. So they are a hallmark of string dualities projected to just a specific order in the low energy expansion. So you can do stress tests of dualities. You can sometimes use duality to infer bits and pieces that are hard to compute. or if you succeeded in computing something at a given loop order, string dualities often help you to uplift this to other loop orders. Yeah, I mean, this is the cool thing about S-duality, that it wildly mixes different loop orders, and furthermore, it's a gateway into the non-perturbative. Maybe I should have made this disclaimer 20 minutes ago, that this only captures power-behaved terms in the string coupling, and there's always a non-perturbative sector beyond the reach of all these worldsheet diagrams. I mean, contributions that go like e to the minus 1 over g string. So it's string dualities that can often be used to convert the perturbative information into the non-perturbative one, which is beyond the reach of these worldsheet diagrams. Okay, so these are the three main reasons to go through all this formalism for string amplitudes. And after these statements of motivation, let me try to get more precise about what these pictures mean and how we translate them into concrete mathematical expressions. So we need, first of all, to settle what are the weighting factors for these different diagrams. I owe you a proper introduction of the string coupling. So the idea is to extend the Polyakov action by one more term. Maybe you are a little bit shocked now, given that I told you many times that there is no extension needed for Polyakov action. Here is one exception to that rule. We haven't looked at Einstein-Hilbert yet. I told you that you shouldn't introduce a potential term, because this is breaking Weil invariance. I also discouraged you from adding a cosmological constant, because also that would break Weil invariance. But we are free to add an Einstein-Hilbert term, denoted by chi here. So this is what you expect from the GR course. Determinant of the metric, and here the Ricci scalar on the worldsheet. So similar to the story with the energy and momentum tensor, this is really the two-dimensional Ricci scalar on the worldsheet, constructed out of the metric H or the Christoffel symbols with indices alpha, beta ranging from 0 to 1. Okay, so this, well, by the standard arguments in GR, it is a diffeomorphism invariant. And furthermore, if you zoom onto the definition of R, you will find an inverse metric. So it's also compatible with Weil invariance, that the inverse metric here will eat up the Weil transformation of the determinant. So this is something we can add. And why am I telling you this as late as now? The reason is that it's actually a topological term, that in 2 dimensions, Einstein-Hilbert Lagrangian is a total derivative. That's exclusive to 2 dimensions. Oops. So as such, it may look tempting to drop it. Quite often in this course, total derivatives integrate to 0. So here, they are not integrating to 0, but instead to a topological term. So already this notation chi is borrowed from Nakahara and other textbooks. This is the Euler characteristics. And yeah, it evaluates to a topological term that depends on the genus of the surface. 2 minus 2g, where g is the number of holes in the above, or with the extra caveat that in the open string case, the topological term really can take integer values and is not necessarily even. Okay, so these are this term here is setting the weighting factors for string amplitudes. So imagine you start constructing the contributions from path integrals where the action goes into the exponent, then there will be additional exponentials of this chi lambda combination. We will talk about these path integrals in a few minutes, but let me already right now write down the formula. So closed string amplitudes with the weighting factors inserted start with e to the minus 2 lambda, the contribution from g equals 0, and then here is genus 0. And now it's also the right time to really draw it as a sphere. I think on this blackboard I don't need to make any connections with Feynman diagrams anymore. So I'm already doing the diff cross vial moves to map the asymptotic states and the associated long tubes and strips to point-like defects, to punctures. Okay, so for the 4-point example above, we have a sphere with 4 punctures. And this prescription to path integrate over different histories, this means concretely that we need to integrate over all possibilities to put 4 punctures on the sphere, but only the conformally inequivalent ones. So that disclaimer goes into the notation here. M04, this is a moduli space of sphere with 4 marked points. And more generally, for all these Riemann surfaces in the closed string perturbative expansion, we need the generalization to MGN. So these are the integration domains for different contributions to closed string amplitudes. Moduli space of compact genus G Riemann surfaces with n marked points. You will see more pictures to exemplify what that is at g equal 1 and 2. Yeah, so here this is about how to put marked points on the sphere. Then genus 1 happens to come with 0 coefficient of lambda in the exponent. So at genus 1, the worldsheet for closed strings, or for 4-point closed string amplitudes, is a torus with 4 marked points on it. And it will have a different moduli space because there is less conformal symmetry compatible with the torus than there is with the sphere. And also there is a complex structure modulus. I mean, there are several inequivalent shapes of that torus that need to be considered. Okay, and then this genus 2 contribution comes from the moduli space of this genus 2 surface, and so on and so forth. Okay, so this is the mathematical concept describing the integration domain for these closed string amplitudes. And then next question is, what does the integrand mean? So what do these funny pictures symbolize? So this is always a correlation function tailored to the respective surface. And it's a correlation function that carries the external state information. And here is where we benefit from the vertex operator description of the spectrum. I mean, here you have a much easier time in processing the field correspondent of the physical state rather than dealing with its oscillator representation. Okay, so there are definitely the vertex operators in there. So this superscript sigma g tries to remind you that different worldsheet topologies give rise to different correlation functions. Like it's more or less different boundary conditions with which you solve the respective differential equations. I will give you examples shortly. And then I left this gap here. There are also certain ghost contributions, or possibly more. So for instance, at tree level, we will see after the break that you need to insert a certain C ghost to it, or a total of 3 C ghosts at tree level. So this is giving you a slightly more precise characterization of the integrands here. And just for completeness, the open string analog of that picture down there is starting with a disk, which looks roughly like that, with 4 external states. And then here, maybe I should finally take the courage to draw a Möbius strip. There is, as discussed before, a cylinder topology with 4 marked points, and now a Möbius strip, which looks roughly like that. Hopefully. Yeah, and then contributions like that for genus 2 and higher. Good. The next section will be about a more precise characterization, like discussing how to actually compute these correlation functions. I guess I have mentioned them too many times and still not giving you detailed prescriptions, though this is going to be the next move. Is right now a good moment for the break, or? Okay, good. Let's make the break now. Mm-hmm. Okay, welcome back. I confess I spent a bit more time discussing the big picture than originally budgeted, so now I will try to gear back to concrete hands-on calculations and try to explain how to compute these individual diagrams and spell out various ingredients of integrand and integral. So these correlation functions that have been mentioned over and over again, I would recommend to compute them via path integrals. So here is a path integral description of correlation functions composed of the free boson as well as its derivatives. So phi is a general placeholder. Maybe it's one of these plane waves. Maybe it's just a holomorphic derivative of x. So for any such combination phi, you can define a correlation function through the following path integral. Path integrate over all field profiles of the free boson X. Put in the Polyakov action in conformal gauge. So just like in QFT, take the exponential of the action as a measure. And then insert all of these fields phi. So again, each of them is welcome to be some plane wave, some derivative, or a mix of all of that. And to make sure we have a good normalization, here is the unit path integral z, or you may want to call it partition function. Okay, and just as a reminder, conformal gauge representative of Polyakov action in complex coordinates has normalization like here. Yeah, in principle you can run this program for arbitrary genus, but here I want to be very specific about genus 0 to cover the sphere and the disk. So how do you convert this path integral description into concrete expressions that will be useful for vertex operators? So let's do one step at a time, and for the moment compute the two-point function. And the two-point function is computed with the axiom that total derivatives in the path integral sense integrate to 0. So if it was a finite dimensional integral, the corresponding total derivative would be partial x, or maybe partial x0, partial x1, and so on. But given that this is now a path integral, the differential operator of interest is this functional derivative. So I mean that functional total derivatives integrate to 0, and there are infinities of corollaries of that. You can cook up a lot of things and take their functional derivatives and use that they integrate to 0. And here, that's the following choice that gives us a differential equation for the two-point function. If you use the fact that this particular total functional derivative integrates to 0, what you get is, first of all, a delta distribution from the d by dx hitting that one. And then, by hitting the Polyakov action in conformal gauge, you get a Laplacian. But now this is a more conventional derivative. This is no longer a functional derivative, so there is no integrate to 0 statement for a partial z. Okay, so what we see here is effectively a differential equation. I mean, both terms can now be identified as a two-point function and a 0-point function, respectively. And with this normalization convention involving the 1 over z factor, the outcome of this analysis is that the two-point function obeys a Laplace equation with a delta function on the right-hand side. And I guess you have seen variations of that in many, many different contexts, say anywhere in quantum field theory. When you want to compute a Green's function, you run a similar trick. So you first derive the Laplace equation of the Green's function from path integral methods, and then you integrate that differential equation. So which function of z and w is kind enough such that its Laplacian gives us the delta distribution. If we were in dimensions 3 and higher, it would be a power law to do the job. And 2 dimensions is very special, where the Green's function associated with the delta source is a logarithm. And given that x itself is democratic between left and right movers, I should make sure that there is really the real analytic combination, log of z minus w plus log of z bar minus w bar. Okay, so this I will refer to as the closed string Green's function. So this capital G closed is representing the logarithm over there. So this is the Green's function on the sphere. And where did I use genus 0? Why am I faithful to the headline here? Well, if I was on a torus or a higher genus Riemann surface, you would need a couple of periodicities. I mean, the torus has these two homology cycles which the sphere doesn't have. You need periodicities for both of them, and, well, just look at the logarithm. It won't have those. This is tailored to the sphere. Yeah, so this is a very simple application of this path integral machinery, but it also allows us to directly proceed to endpoint functions, not only of the x field itself, but also for the plane waves. All the vertex operators were constructed to have one of these plane waves. And since I told you before the break that you need endpoint functions of vertex operators for scattering amplitudes, it's clear that the endpoint function of those is on our shopping list. Yeah, so let's use path integrals to compute this endpoint function here, allowing for different momenta p1, p2, ... all the way to pn. And yeah, once more, the opening line is to path integrate the Polyakov action, or its exponential, together with everything which is inside the angular brackets. And yeah, amusingly, everything is exponential. There is first of all that exponential from the plane waves, and then there is the exponential of the Polyakov action. So I'm writing this out in all detail to convince you that this is actually a Gaussian integral. Never mind the fact that we are doing path integral, rather a finite dimensional integral. It's fortunately a Gaussian, where the integrand is an exponential with terms linear and at most quadratic in the integration variables x. So there are a couple of standard moves where I hope you have seen variations of them in quantum field theory courses, evaluating Gaussian integrals, also Gaussian path integrals. You find after a couple of steps that the outcome is again an exponential. And as always for Gaussian integrals, the key is to get the inverse of the operator in the quadratic term. So we need the inverse of this differential operator here, pretend it's a matrix, and write down the formula with the matrix inverse from the finite dimensional case. But yeah, the inverse for a differential operator is the Green's function. So here, this is where the GCL from the other board enters. So you stick in all pairs of Zi and Zj. Yeah, this sum over all the insertions, it comes from the shift of the integration variable. I mean, if you want to complete the square here, you must somehow absorb the information on the Zi and the momenta in shift of the field x. So that's the reason you will eventually get the closed string Green's function at all of these points. Now, here is one extra term which has to do with the zero mode. So to justify this extra term, let's keep in mind that the path integral contains, among other things, a finite dimensional integral over zero modes. So I hope you can distinguish my little x for the center of mass position from the capital X for the worldsheet field. And also the plane waves have a zero mode contribution. So also here, the capital X in the exponent of the vertex operator contains, among other things, the little x. So that finite dimensional integral over these plane waves involving center of mass positions, this is the reason why you get this delta function. Yeah, and what it does, it's momentum conservation. One of the most basic things about Feynman rules is that each Feynman vertex imposes momentum conservation for the incoming and outgoing lines. And here in the string amplitude setting, this delta function comes from the plane wave parts of the vertex operators and from this finite dimensional slice within the path integral that defines the correlation functions. Okay, then let me give you an even more processed form of this endpoint function. I mean, you saw an expression for the closed string Green's function. This is a logarithm, and clearly having an exponential of logarithms that calls for further simplification. So when the dust settles, what you really have is all these differences of zi and zj raised to these powers. Okay, and then a last remark for those who are worried about logarithm of zero. Well, we don't have any logarithms of zero. It has to do with the fact that we start out with these normal ordered exponentials. It's always forbidden to do OPE contractions between fields at the same position. So as a consequence of that, you will never have to feed the Green's function twice with the same marked point. That's why the double sum excludes the diagonals. And yeah, I have rearranged that double sum into an ordered double sum with I strictly smaller than j. Yeah, so this plane wave correlator is the backbone of all tree-level correlation functions and ultimately of all tree-level amplitudes. I will repeatedly refer to it and call it the Kober-Nielsen factor. And it's universal to any collection of external states in these tree-level amplitudes. I hope I wasn't misleading you to, with the emphasis I put on the massless states. You can, of course, put any collection of states in the string spectrum into that amplitudes prescription. And all of tachyon, graviton, gluon, and massive states will have this as part of the vertex operator. So that's why that Kober-Nielsen factor is so universal. And I want to be clear about the nuances in the open string counterpart. If you want to repeat all these exercises on the sphere for the disk, then you have to think about the Green's function for a minute. So here I want to tell you about how to get the Green's function on the disk from that on the sphere. The Laplace equation, which we derived up there, is in fact universal to sphere and disk. But the difference is in the boundary conditions that you supplement to solve the Laplace equation. So here I'm writing G open for the Green's function of the disk, and I even need to distinguish Neumann and Dirichlet directions. So both of them will follow the Laplace equation that we already had on the sphere. But now the difference is Well, not only in the boundary conditions, but also in the domain. I mean, the open string worldsheet was sent to the upper half plane using this exponential map. So you impose this Laplace equation to hold for z and w in the upper half plane. This takes into account that we are discussing the disk now. And yeah, as I was saying before, the key difference is in the different boundary conditions. That in the Neumann case, you want to respect the vanishing sigma derivative at the endpoints, which in our complex coordinates takes this form for Neumann. So this is, as I explained yesterday, the sigma derivative. And likewise, Dirichlet boundary conditions just flip the sign such that these derivatives here give rise to a tau derivative. Yeah, so these are the boundary conditions, but now they are not in the upper half plane, like where the Laplace equation is imposed, but only for real z. We have to impose these boundary conditions. Yeah, so this feels a little bit like back in the days where we attended an electrodynamics course and studied boundary value problems. You are given a differential equation, so here second order equation similar to the Poisson equation of the electrostatic potential. And then you are told where the potential or its normal derivative is supposed to vanish. So it's a ubiquitous problem in mathematical physics to solve this boundary value problem. And we can borrow the method used in electrostatics, namely the method of image charges. It was quite important for these problems in electrostatics that you usually impose the Poisson equation only in a certain region of space. So you can afford to violate the Poisson equation elsewhere in a region where you don't look. And the same trick works here, method of image charges. In order to make sure you satisfy the boundary conditions, you add image charges outside the open string worldsheet. So here in the Neumann case, for instance, you simply combine closed string Green's function for z and w. They are both in the upper half plane. They are both fit to solve the Laplace equation on the worldsheet. And then here comes the image charge, a closed string Green's function pairing z and w bar. But given that z and w bar are confined to the upper half plane, they never meet so they never screw up the differential equation. So with these arguments, you find as a closed string Green's function, as a Green's function on a disk, the combination of two terms. The first is the same logarithm that we had in the closed string case, combining the meromorphic z with the meromorphic w. But now as a contribution from the image charge, there is now a second type of logarithm which combines z and w bar. Okay, so this is the solution to differential equation on the upper half plane plus boundary conditions. And it's just a matter of tweaking the relative sign to also accommodate the Dirichlet boundary conditions. Yeah, so if you insert that into the Kober-Nielsen factor, then it will double the exponents. We had this closed string Kober-Nielsen factor with exponent 1 times alpha prime p dot p. And now in the closed string case, where the Green's function is composed of two logarithms, then you will get an additional factor of 2 up here. Of course, I'm using the fact that for open string Cobra-Nielsen factors, these z's are lying on the disk boundary and are therefore real, such that the two logarithms here degenerate. So here, the assumption is that all these z's are indeed open string insertion points. Oh yeah. And yeah, as I was saying, these Green's functions here are special to genus 0. If you are asking about genus 1 Green's functions or higher genus Green's functions, I would have to solve a Laplace equation similar to that with more periodic boundary conditions. Periodic for each of the homology cycles on the higher genus surface. And that requires a few more tricks, more specifically Jacobi theta functions, which generalize trigonometry to not only have one periodic direction, like the sine and the cosine, but to have maybe 2 periodic directions in case of genus 1, or to have 2G periodic directions in case of genus G. Yeah, so if I had more time, I would happily give you an excursion into Jacobi theta functions, but let's maybe prioritize other things for now. Yeah, so this path integral exercise was only looking at the field X. It was only looking at the gauge-fixed Polyakov action, but I was sweeping the prehistory a little bit under the rug. How do I get into conformal gauge when everything is phrased in terms of path integrals? So this I try to explain better in the section here on ghosts. And I'll try to be ambitious and tell you about ghosts at different genera, at least a couple of qualitative features that are supposed to be true also at higher genus. Yeah, so it's really about filling an omission that is in the origin of that path integral formula with conformal gauge Polyakov action. How is diff cross Weil invariance fixed in order to get there? So let's roll back to Polyakov action at a generic worldsheet metric. And if you're asked to do path integrals with the H-dependent Polyakov action, you may have the following first idea. You may think about path integrating not only over X, but also path integrating over H. And I think I've almost provocated that by telling you before that amplitudes are obtained from path integrating over all histories. So why not think about H's as being part of all histories? But then there was the important disclaimer, only inequivalent histories under the symmetries. Only inequivalent configurations of X and H under the diff cross Weil invariance of the Polyakov action. Yeah. Since I will use this object all over the place, I need a notation. So let's again use a Z, but let's decorate the letter Z's to make sure you're not mixing it up with the earlier partition function. Yeah, so this problem here arises at each genus, how to make sure you're only integrating over diff cross Weil invariant matrix H. And for the moment, this is a very formal prescription here that denominator is something like a call for help. I need to think more carefully about how to mod out by diff cross Weil. So how to compensate for the overcount if I were to integrate over all configurations of X and H. That's pretty serious because it's an infinite overcount. So here, for the moment, all that the denominator says is that we need a way to compensate an infinite overcount. But yeah, in the end of the day, this infinite overcount, it's a 0 over 0 problem. At the end of the day, the multitude of diff cross Weil images in the numerator cancels against the huge number of diff cross Weil transformations in the denominator. So roughly, all the infinities cancel, of course, between the path integral over the matrix and this inverse volume. But it doesn't cancel straight away. So there are a few caveats. You cannot just cross them out, but let's take a breath and think about how we would do this in terms of change of variable tricks when you integrate. So what you want is, you want to line up the integration variables up here, the different field configurations. You want to line them up with the parameters in a diff cross Weil transformation. So you want to transform the path integral variables here for the metric in the numerator. You want to line that up with parameterizations of this diff cross Weil symmetry. Yeah, so there is something like a change of integration variables going on in the path integral level. So if it was a finite dimensional integral, you would just say, yeah, we need a finite dimensional Jacobian. But here, this is a path integral, so to say an infinite number of ordinary integrals. So we need a functional version of a Jacobian determinant. So this is Jacobian, which maybe you saw the same circle of ideas in the quantization of gauge theories. This is a so-called Fateev-Popov determinant. And yeah, it comes from the change of field variables that you need in order to cancel the things against one another. Here, change of field variables. Okay, so there is something like a finite leftover from doing this change of field variables. Concretely, it's some Fateev-Popov determinant. And now the question is, are we removing all integrals relating to h like that? And this is the moment to lift all the mystery about the buzzword local. I think I stressed several times that only locally you can do the following. You can only locally gauge fix the metric in the Polyakov action to the Minkowski one. It only works at genus 0, but if you're at genus 1 and higher, there are some global obstructions to do that everywhere. Or putting it differently, there are some finite dimensional integrals left to do that hop out of the path integral for h. So here is that extra integration that you need to do when the genus is 1 or higher. Here there is a finite dimensional remnant of dh after modding out by diff cross Weil. It's a pity that I'm running out of blackboard right here. Finite dimensional integral. It should really be on the same blackboard. My apologies for playing that trick here. Over complex structure moduli. Some complex variables tau that describe different shapes of the surface different choices of the metric that are not related by a diff cross Weyl transformation. I will give you an example. So, morally speaking, this is about different shapes of the surface. And the first time where this is non-trivial is for the torus at genus 1. So how does this z objects above, the Polyakov path integral, how does it look like at genus 1? So from what you heard before, there will be an insertion of a Pateev-Popov determinant, which I will also spell out. And now, ideally, we would like to completely remove the path integral over metrics. Ideally, I would skip everything related to dH. But, as I'm telling you here, there is still a finite dimensional integral left. And here, it's a single complex structure modulus tau, which tracks the following, which tracks different shapes of the torus. Different shapes that you cannot remove by diff cross Weyl. And here is something very concrete that you cannot change by diff cross Weyl. So let's draw here the homology cycles of the torus, an A cycle and a B cycle. And the ratio of their lengths, this is something that you can't modify using diff cross Weyl. So this complex structure modulus in case of the torus is the ratio of the B cycle length and the A cycle length in that picture. Oops. So one typically normalizes the A cycle to be of length 1. And yeah, this is the variable that needs to be still integrated over as a remnant of the path integral over metrics at genus 1. Okay, and then there is the Polyakov action. Yeah, but for each tau, there is still a kind of optimal metric that you can choose. I mean, if it wasn't for the taus, I would say just use the Minkowski metric. I mean, on the sphere, you would then evaluate the Polyakov action in conformal gauge. And in the scenario beyond genus 0, then let's say for each choice of tau, there is a kind of favorite choice that you can make for the metric. So that's why I'm writing h of tau in both cases. Yeah, and the analogous story at higher genus will simply involve more such complex structure moduli. If you think about possible shapes for a genus 2, genus 3, genus G surface, then what one finds is a total of 3G minus 3 complex structure moduli. Okay, I admit this is probably not particularly obvious, but that's a result from mathematics of Riemann surfaces that we can borrow. So then there's not only a single tau, but let's just label the tau with j equal 1, 2, 3, ... all the way to 3g minus 3. And accordingly, the analogous expression will have a larger number of such d squared tau integrals. Yeah, so this is to spell out the number of finite dimensional integrals that are left to do in this Polyakov path integral. But I have not yet given you the actual expression for the Pateev-Popov determinant. And okay, to convey the key ideas of that, it's probably enough to be at genus 0 for the moment. mean, the Faddeev-Popov determinant is already non-trivial at genus 0, where we have no such complex structure integral. And the only difference to the previous path integrals is in this delta Fp. Okay, let's see, time is running. Yeah, perhaps I might need 10 minutes to finish that off. Is that? Okay, let's go speedy. Yeah, so this will give rise to the ghost system, Grassmann-Ott ghost variables, whose path integral gives rise to this Faddeev-Popov determinant. B and C, both of them being Grassmann-Ott. And the idea is, well, this delta is a determinant. And determinants notoriously come out of Gaussian integrals. Well, the bosonic Gaussian integrals, strictly speaking, give you an inverse determinant. But that one is not inverse. This is a numerator determinant. So to make sure that the determinant lands in the numerator and not in the denominator, you will have to pick Grassmann-Ott fields, B and C. Because if you compare Gaussian integrals over Grassmann-Even and Grassmann-Ott variables, the key difference is that the determinant lands in the denominator in case of Grassmann-Even and in the numerator in case of Grassmann-Ott. So that's the reason that these fields have to be chosen to be Grassmann-Ott. Okay, so in the first pass, I will leave the metric generic. It is true that you can choose the metric to your favorite value. And so far, I haven't committed whether I like the conformal gauge or whether I would prefer a different choice of metric. So in the first place, this makes sense for any choice of your favorite metric. So in each case, you have completely collapsed the path integral over the metrics, and you just use this one for the same choice of metric that you make for the Polyakov action. And yeah, so this is now a Gaussian path integral, which is engineered to precisely give you this Faddeev-Popov determinant. And in conformal gauge now, this, of course, can also be fed with the Minkowski metric in 2 dimensions, giving you, for the complete Polyakov path integral, the following thing: path integrate over both the good old matter field X and then also the ghost fields. So there is a total action composed of the Polyakov action in conformal gauge for X, and now the ghost action for B and C, namely that one simplified to a conformal gauge, which yields, now it's 1 over pi. This rather simple expression. And well, initially there were some indices to B and C, and now in this final formula, the indices are gone. Well, this simply reflects my choice that the B without indices is the ZZ component of that tensorial B, and the C without indices means that I pick the Z component of that vector, C superscript beta. And similar story to B bar and C bar. This is about the Z bar components of the respective vectors and tensor. Yeah, actually the B alpha beta tensor is symmetric and traceless. That's why the ZZ component and Z bar component for B are enough. Now, all the efforts to explain CFT basics will also pay off in the ghost context. So also the ghost system is a CFT. So a lot of the wisdom applies right here as well. So that ghost action also defines a CFT where the underlying energy momentum tensor can be computed in principle from up here. Knowing the action for generic choice of metric, you can determine the energy momentum tensor by variation with respect to the metric. And after variation, you can, of course, go into conformal gauge, which in that case yields this normal ordered product of a B and a C and a derivative. And you can follow the steps that we did yesterday for the free boson to compute various OPEs between energy momentum tensor and the fields. Of course, you need in the first place the OPE among the individual ghosts. This is the starting point in everything. And this is something you can get from the action. But once you know how B is OPEing with C, then you can use the Wick rules to determine the OPE of the energy momentum tensor with either of B and C and itself. So by following the steps using Wick theorem that we went through in the case of the free boson yesterday, you will...
Does the 2 multiply just the first term or both?
Only the first term. Following these steps, you can read off conformal weight 2 for the B ghost. So this is from the double pole residue in the OPE of T with the B ghost. And similarly for the C ghost, you find residue -1 on the double pole. And now it's a bit unfortunate that the letter C, like Caesar, is overloaded. So a C without any decoration is a ghost variable. And now here, the C with subscript GH refers to the central charge obtained from the quadruple pole of the energy momentum tensor. And maybe this is a bit hard to believe, given that the energy momentum tensor looks so tame. But yeah, if you grind through itself OPE very carefully using the Wick rules, then you will find a residue -13 of the quadruple pole of T of Z with T of W. And yeah, in general, CFTs, we use the notation central charge divided by 2 to refer to the quadruple pole residue. So we can read off central charge -26. Yeah, I think I should relegate that discussion to the next lecture to emphasize that this determines the critical dimension of the bosonic string. So I will tell you in the next lecture why it is quite important to cancel the central charge of the ghost with that of the matter system. The last thing I want to say before lunch is how to deal with the zero modes of the BC system, or what are the subtle differences when you go from one genus to another. Since these are Grassmann odd variables, it's particularly delicate to think about the fermionic zero modes. I mean, for each mode, this is a Grassmann odd integral here, and as you know, Grassmann odd integrals want you to have one insertion of the integration variable. So for each zero mode hidden inside that path integral, you're obliged to insert one such zero mode. Otherwise, the path integral gives 0. So there is a genus-dependent story to how many zero-mode integrals are hidden here. And it's easiest to state the relative number of zero modes associated with the C ghost and with the B ghost. Namely, the difference of them is the following genus-dependent quantity, 3 minus 3g, by the so-called Riemann-Roch theorem. There is a lot of mathematical material that comes to rescue of a string theorist here. So if you want to read about this in all detail, then you can, for instance, consult section 6.2 in Blumenhagen-Lust-Theissen. Okay, so this is the zero-mode content, which is part of that path integral. And yeah, fermionic zero modes are a very, very strict filter. It sets to zero all correlation function, which doesn't saturate all these fermionic zero modes. So in other words, there is a big bunch of vanishing correlation functions. Because of that, these ghost correlation functions are zero unless you dial the ghost insertions to fit to the zero mode counting. So let me write this a bit more formally, that you need to dial the ghost charges to be compatible with this zero mode counting. You want the ghost charges to add up to, number of B ghost insertion minus number of C ghost insertion should better be 3g minus 3. Otherwise, the correlation function is zero. And when I use the word charge, maybe this is a bit confusing to you. Maybe some of you are tempted to interject, normally charges want to be conserved. Shouldn't you get zero if you want to see a charge getting conserved? But here we demand something non-zero, and one thinks about this like a background charge that needs to be cancelled. So in absence of any ghost insertions, there is a background charge to the vacuum, which needs to be cancelled by the charges of the insertions here. So this can be phrased as a cancellation of background charge. And there's a similar background charge to the ghost system of the superstring that I try to show tomorrow. Okay, now it's definitely lunchtime. Really sorry for going over time.